Hi everyone, and welcome to this session on geometry and optimization. Our first paper is sampling from Quadric-Based CSG surfaces, and it's by Philip Trettner and Leif Cobell.
Hello.
Hi, Philip.
Hi.
And I believe it's pre-recorded, so I think it's just going to magically start playing in the background.
Hello and welcome to my presentation. I'm Philip Trettner and we present a method to sample efficiently from Quadric-Based CSG surfaces. In this context, CSG means constructive solid geometry, and it is a natural and quite ubiquitous paradigm, especially in solid modeling, in 3D modeling, and even in level design. For the sake of this presentation, approaches to CSG can be roughly categorized into those that try to compute a geometric representation, and there's a long list of methods that do these. And this can range from mesh representations over volumetric representations such as binary space partitionings or voxel grids. However, the problem is quite challenging and it is hard to wrap these methods into an interactive setting, which is why there's a second class of approaches that try to compute a visualization only. And here there is also a long list of methods that approach that. Our method is kind of a hybrid of these two classes. We have two components. First, we compute a sampling of the CSG surface and then return these samples into a hole-free and pixel-perfect rendering. And with that, it's kind of a hybrid because we have a geometric representation in this point cloud, which is not as accurate as a mesh representation might be, but it still is useful, for example, for collision detection. But then a big focus is also on making the rendering fast and high quality. The first part, the sampling part of our method, starts with the CSG graph, which has leaf nodes, the primitives that are quadric surfaces in our system. And our method can now sample more or less directly from the CSG surface, and we use an adaptive sampling scheme to make this really efficient. We then take these samples and render them as splats and introduce a local quadric ray tracing and clipping scheme to make this hole-free and pixel-perfect in the end. Okay, let us start with the sampling procedure. The primitives in our system are quadric surfaces, and as a reminder, a quadric is usually represented by a symmetric 4x4 matrix, and the quadric surface is then the zero isosurface of the quadratic function x.qx. The different types of quadric surfaces depend on the eigenvalues of q, and quadric surfaces are actually a superset of many of the classical primitives. So we have spheres and ellipsoids, we have cylinders, cones, planes, and even some more exotic ones. And another property which is really useful from the perspective of a 3D modeling system is that quadric surfaces are closed under affine and projective transformation. Any 4x4 transformation matrix can be multiplied and applied to the quadric and results in a new quadric surface. Now, given these primitives, we can combine them using a graph of Boolean operations. So for example, these two spheres can be combined using the intersection to yield this lens-like shape. And then we can add a third sphere and union it into the lens to get more and more complex CSG objects. Okay, let us continue with a basic intuition, a high-level intuition of our method, and then we will see how we make that more efficient. So from this previous example, we have an arrangement of quadric primitives. And now our method takes each of these primitives and generates samples on them. Each sample can then be classified using the CSG graph, and the resulting classes are samples that are either outside, inside, or on the CSG surface. And then finally we discard the non-surface parts, and that is a sampling of the CSG object. However, in this formulation, the method would be quite inefficient, as in general we would discard large areas of samples. And also, if samples are generated independently, it's really hard to guarantee a whole free rendering in the end. So this is only the high-level concept of our method, and now we will make this efficient and also have good guarantees. And for that, our method works in 2 steps. It's basically the pipeline of our method. First, we take each quadric surface and analytically partition it into a set of low distortion height fields. From these height fields, we can then start an adaptive sampling and subdivision scheme, which will efficiently narrow down to the areas where generating the samples is actually needed to generate surface samples. So let's continue with the low distortion height fields. We take a quadric surface and compute an eigenbasis of the quadric matrix. And this is a natural coordinate system of a quadric. In this coordinate system, we can take each coordinate plane and shoot a ray perpendicular to it, either in the positive or negative direction, and intersect that with the quadric surface itself. The result is that we get 3 different height fields. And because this is the eigenbasis, many of the terms simplify, and we get a really compact description of the height field. So just the square root of a simple quadratic function with 3 coefficients a, b, and c that depend on the quadric matrix. Each of these height fields could be used in theory to parameterize the whole quadric surface. However, we get a large distortion in many regions. And similar to how triplanar projection mapping works, we now strive to only take those regions that have the lowest distortion. So we take the parts of the height fields that are the lowest distortion region from the set of the 3 possible height fields. The details of that are in the paper, but just to give a high-level intuition, if we take height fields of this form, there are only 5 types of possible configurations that depend on the signs of A, B, and C. And here in this visualization, blue means that this part of the height field is actually the lowest distortion possible, and gray means that one of the other 2 directions yield less distortion. And again, the details are in the paper, but what we derived are analytic boundaries of these regions. And it turns out that these are also conic sections in 2D, and we were able to derive their formulas by looking at the normal component of the height field. So this in the end yields 9 different types of triangles, of potentially infinite triangles. And to make this easier to process, given the bounding box of the whole sphere scene, we can actually classify or subdivide the height fields into these basic regions that are now all bounded. So each quadric surface is decomposed into these basic regions. These basic regions, they live on the coordinate planes, and if they are projected back onto the quadric surface using the height field function, we get a decomposition of the whole quadric surface. And each of these height field regions has an area distortion, which is at most square root 3. So this is the decomposition into low distortion height fields. And this is the starting point where we will now drive an adaptive sampling and subdivision scheme that will narrow down and discard regions where we don't need any samples at all. By design, each basic region is part of the quadric surface. However, it might not be part of the CSG object. So in the easiest case, it actually is part of the CSG surface. So in this simple example, the basic region belongs to the light blue quadric surface. And here the basic region is completely part of the resulting CSG surface. And we don't need to subdivide further because we can just generate samples in this basic region. Even simpler, if the basic region is completely outside or completely inside the CSG surface, we can also stop the subdivision and don't generate any samples at all. Only in the case where we have a mixed classification where some parts are outside and some parts are part of the CSG surface, we need to actually subdivide. So given such a classification, if the basic region is fully part of the CSG surface, we use a rasterization-inspired scheme to place samples on the basic region in a way that they cover the region completely, so that if we're rendering those later as splats, there will be no hole in our surface. If the CSG, if the region is completely inside or outside the CSG surface, we simply discard the region. And finally, in the case of an inconclusive classification, we use a longest edge split to recursively subdivide and then reclassify each region. Still, there is the question how the basic regions are actually classified, and the basic ingredient for that is a distance query, a distance to quadric surface. In general, this is a really challenging problem. For spheres, there are closed form solutions, but even for ellipsoids, one typically has to use an iterative scheme to get to an accurate solution. Luckily for us, we are not interested in completely exact distances, and a conservative approximation is sufficient. And that's what we derived in our paper. We derived an efficient and practical bound for the signed distance to quadric surface. What that means is, given a quadric, we can now place queries anywhere in the space. And if we're querying a point outside a quadric, we get a radius where everything inside this radius is guaranteed to also be outside the quadric. Symmetrically, if we're querying inside a quadric, we are getting a radius where everything inside this radius is also inside the quadric. These are actual values here, so that is representative of the quality of our approximation here. And it is really efficient to evaluate, requiring only a single quadric evaluation and a univariate quadratic equation. We were even able to prove another desirable property, that the distance, or this bound, converges to the true distance the closer we get to the surface. How these basic distance queries can be combined to classify the basic regions is further described in the paper. Now, if we have this subdivision scheme, just to give you an idea how this looks like in practice, for this simple 3-quadric object, each of the quadrics has an individual subdivision pattern. And our scheme is able to skip over uniform regions, or regions where the classification is uniform, which means regions that are completely outside or completely inside the quadric. They are largely skipped over and don't generate any samples at all. But even regions that are part of the surface but are uniform in their classification can simply switch to this rasterization-based covering algorithm and don't have to use the more expensive subdivision scheme. And only in those regions where multiple quadrics interact do we actually need to subdivide. And that's where we then focus our classification performance on. This concludes the sampling part of our method. I will now briefly present how we turn the samples into an efficient, hole-free and pixel-perfect rendering. We start by rendering each sample as a flat splat, where we take the normal based on the quadric surface. Here in this visualization, we applied a reflective material with an environment map so that we can judge the surface quality. And here the quality is still quite low because the splats are flat and quadrics in general are smooth curved surfaces. So the first thing we introduce is a local quadric ray tracing procedure where we reproject each splat in the fragment shader onto its generating quadric surface. This results in a smooth surface appearance, but we still get artifacts when multiple quadrics interact, where we get these seams or overhangs. And we fix that by employing a local quadric clipping procedure. So let's start with the ray tracing. Each splat actually knows which quadric primitive it was spawned from. And in the fragment shader, we have access to the current view ray. So we can now intersect this view ray with the quadric primitive. The view ray is a linear function, the quadric is a quadratic function, so we can solve a simple quadratic equation and get up to 2 intersections. If we have no intersection, we discard the fragment, and if we have multiple intersections, we take that intersection that is closer to the sample. That gives us a smooth surface appearance, and then we use the clipping to get rid of the overhangs. So here the scenario is that we have, for example, this splat here, which is on a quadric A, and this splat should be cut off because we have an intersection with a quadric B, but if we're not modeling that, we get this overhang. So if we know that B is an intersection, we can evaluate the void position of the fragment with respect to quadric B, and if that is positive, it means that we're outside B and we discard the fragment. Now we don't want to check every fragment against every quadric in our system, so instead we use the conservative distance function, these bounds that we derived earlier, to limit the set of potential clipping quadrics. So we have for each splat, we know which quadrics are potentially interacting. If we have a splat here, there would be no quadric interacting, and for this example splat, there is a single quadric. We deduplicate these sets so that the overhead per splat in the end is only roughly 2 indices, and the result is a really efficient clipping procedure. So most parts of the surface don't have any clipping at all. At edges, we get usually 1 clipping evaluation, and then only at corners do we have 2 or more of these evaluations. Taken together, we have actually quite strong guarantees in our system. So the adaptive subdivision sampling procedure guarantees hole-free rendering because it guarantees that for every part of every point on the CSG surface, there's at most 1 splat on the same quadric within a certain user-provided distance. And then we use this local quadric ray tracing and clipping to generate a pixel-perfect hole-free rendering. And here, even if the splat size is relatively large, it causes no issue with really small features that are modeled. So, how fast is our system? Here we see a selection of our evaluation from low complexity to higher complexity. And for each of these models, we evaluated different numbers of samples. The sampling was performed on a single CPU core, and for models with lower complexity, we have up to a few tenths of milliseconds to generate the samples, and for the higher complexities, a few hundreds of milliseconds. This translates to a few million samples per second per CPU core, and it is actually quite straightforward to do a parallel implementation of this. This is only a pre-processing step, because then we can render the scene from any point of view without resampling. And this is something that we're really proud of, the rendering time of our method, which is consistently below a single millisecond for full HD on a high-end card. This is because the clipping has little overhead, we only have this single ray tracing per splat, and it turns out to a really efficient method. We compared that using a ray tracing implementation, a pure ray tracing implementation, where in a fragment shader the whole CSG tree is ray traced. And here for low numbers of quadrics, the time is comparable, and then this quickly scales up with the complexity, while our method is largely independent of the complexity of the model and is more sensitive to the overdraw due to depth complexity. The number of splats here actually has no impact on the visual result because of the strong guarantees of our method. However, for practical reasons, it's still neither a good idea to have too few or too many samples. Using too few samples, the render time actually goes up a bit because this results in larger overdraw. And also, if the samples are used for other geometry processing tasks, then the user usually wants a certain minimal distance between the samples. Using too many splats is also not a good idea because that will increase the rendering, the sampling time for one, but also the rendering time, as these the larger number of splats are smaller triangles, which is then less efficient to rasterize. In the future, we want to extend our method with more primitive types like meshes or freeform surfaces. And when we want to model or use our system in larger scenes, it makes a lot of sense to use a graph level spatial acceleration structure. Currently, we are optimized for many locally interacting quadrics, but for larger scenes, such acceleration is a must-have. Also, in larger scenes, it might make sense to look into partial updating if only parts of the scenes are changed, and progressive sampling, where the number of samples or the sample density might depend on the distance to the camera, maybe with some hysteresis. Finally, we are already quite happy with the rendering performance, but one could make it even more predictable by using some occlusion culling, which would reduce the overdraw issue even further. And finally, I already said that we currently only have a single core implementation, and a parallel implementation is quite straightforward to do. So in conclusion, we present a novel approach to efficiently generate samples directly on CSG surfaces. We do that by decomposing each quadric surface into a set of low distortion height fields, which is then the starting point for an adaptive sampling scheme that guarantees a strong surface covering, which can then be rendered using local quadric ray tracing and clipping. And the result is a pixel-perfect, hole-free, real-time rendering of the CSG surface. Thank you for your attention.
Okay, so if anyone has any questions, feel free to jump into the queue. I'll start off with a quick question. You mentioned that you were thinking of, for future work, you were talking about parallel implementation. I was kind of curious, but the GPU implementation is parallel, I guess. So I was kind of wondering,
yeah, parallel means the sampling in that case. So the sampling is single core. The rendering is obviously parallel. The parallel implementation that we are looking for the sampling, especially at the level of these basic regions, it would be quite trivial. So each basic region can be processed in parallel, and that should be sufficient for most systems.
So I was wondering the trade-off with the smaller splats, which give you higher performance, of course. What was the sort of impact on the image quality?
There is no impact on the image quality because the guarantees mean that really there's a pixel-perfect reconstruction of the represented CSG surface. It's the same result in the end. It just means smaller splats will have more overlap and more overdraw, more things that are discarded, so it's slightly less performant.
Yeah. So yeah, why don't? What's the disadvantage with just going with the largest splats all the time?
For the rendering, I would say there's close to no disadvantage. If you need the splats for some other processing, then probably the holes are too big. Yeah. There's a question in the chat.
Yeah.
So the memory footprint is really low. So each splat has an index for which quadric it spawned from and 2 indices to capture the list of clipping quadrics and a free position. So it's like 6 times 32-bit per splat, and then multiplied by the number of splats. So a few tens or maybe a bit or more than 100,000 splats usually.
Okay. I think if there aren't any questions, we might move on to our second paper. Thanks again, Philip.
Yeah, thank you too.
Our second paper is a half-edge refinement rule for parallel Catmull-Clark subdivision by Jonathan Dupuy and Kenneth Van Huey. I think we can start it up, and hopefully Jonathan will jump in while you're watching.
Hello everyone, I'm Jonathan, and this is a presentation for my HPG 2021 paper co-authored with my colleague Kenneth. The paper introduces a novel Halfedge-based refinement rule to compute Catmull-Clark subdivision in parallel, possibly on the GPU. So to start things off, I'd like to briefly explain what Catmull-Clark subdivision is and what it's useful for. So it's essentially an algorithm that takes as input a control cage. So a control cage is a low polymesh such as this one. And given this control cage, it produces a smooth surface, which is visualized here. And the way this is done is by actually successively refining the control cage into these quads that get smaller and smaller as the refinement is repeated. So it turns out that this algorithm produces an exponential number of these quad faces. So for instance, given this control cage here composed of 8,000 faces and 10,000 vertices, you are dealing with, after 4 levels of refinement, with over 2 million quads and vertices. So in order to process such large amounts of geometry, it's important to have a efficient implementation, and a way of achieving this is by deriving a parallel implementation that you can actually run on your GPU. So back to the presentation. So this is the control mesh I just showed, and the subdivision surface computed out of it. And here's a couple of instances just to show how rich and detailed the subdivision surface is. So why did we look into this in the first place? Well, it turns out that nowadays subdivision surfaces are used everywhere, especially in production, but also in video games. And so naturally, most interactive editing tools support it. And the way they do so is by actually using Pixar's Open Subdiv library, which unfortunately has a pretty severe limitation in that it's restricted to fixed topologies. And the reason for this is because it's actually built on feature adaptive subdivision, which is a paper by Niesner and colleagues that was introduced a few years ago. And the way this works is it actually pre-processes the control cage using the CPU, and the pre-processing stage uses it to create a bunch of bicubic patches that can be evaluated analytically to immediately evaluate the limit surface produced by the subdivision. So in terms of rendering, it's pretty efficient, but the pre-processing stage is particularly slow. So for instance, here I'm showing the armor guy I just demoed a few seconds ago, and you can see the result of the pre-processing stage, which creates these bicubic patches pretty much everywhere. And in certain areas, it has to subdivide it preemptively to produce a smooth surface. And it turns out that this pre-processing stage is really slow on this particular asset. It takes over 10 seconds on my laptop, which obviously is too slow for an interactive modeling experience where you expect the user to be frequently editing the topology of his assets. So in this paper, we introduce an alternative algorithm that supports dynamic topology. And the way we do this is by introducing this so-called Halfedge-based refinement rule that allows us to compute the subdivision efficiently. In terms of performance, it turns out that we are able to achieve 4 orders of magnitude speedups with respect to OpenSubdiv on dynamic topology, and for the case of static topology, which is what OpenSubdiv is built and optimized for, we run pretty much at the same speed. So going back to my interactive demo here, I'm just going to show you some results. So here, I'm going to animate the mesh. And here, the subdivision takes roughly 3 milliseconds on my RTX 2080 GPU. And here, the subdivision is computed as if the topology wasn't static. So everything is computed from top to bottom. It turns out that this animation is in fact fixed in terms of topology, so OpenSubdiv could render it. And so if I use this assumption, we have less computations to do, and our algorithm is pretty much faster because there's less computations, obviously. So this is what our demo delivers, and it's the source code that we used for our paper. So how did we do this in the first place? So rather than pre-processing like OpenSubdiv does the input mesh, we just had a look at the original Catmull-Clark refinement rule. So that produces these quads that get smaller and smaller and produce a smoother surface. And what we did very simply was to add a bunch of arrows that actually denote half edges. So they're an additional geometric entity that we considered for this project. And what we realized was that when we submit these arrows to the refinement rule, there's a very simple property that emerges, which is that the number of half edges after each refinement step is multiplied by exactly 4. And this is quite powerful because it's invariant and it works even if the underlying mesh has non-quad faces. For instance, here you have a triangle and a pentagon, and the number of half edges is multiplied by 4 anyways. So based on this simple observation, we derived our entire paper. So this is pretty much the insight, the main insight I expect you to take away after this presentation. Very easy though. And so based on this observation, what we did was to devise a 1-to-4 mapping of each half edge that we could compute in a breadth first order on a parallel processor such as a GPU. So the rule is pretty simple. What we expect is that each half edge splits into 4 half edges that build a quad face. So for instance, this red half edge here is split into these 4 ones, this blue one into these blue ones, and this green one into these ones. Okay, so for those of you who are not necessarily familiar with half edges, so a half edge data structure is essentially a data structure that provides these 6 following operators. So there's twin, next, pre, vert, edge, and face. So twin is given a half edge, you should be able to retrieve, if it exists, the opposite arrow with respect to an edge. Next and prev are the next and previous half edge within a given face. Vertex is the vertex on which the arrow sits. So for this red arrow, this would be the vertex. The edge is this one for the red arrow once again, and the face is obviously the face within which the half edge exists. So to derive our implementation, we had to provide a way to evaluate these operators. So usually these are done using C++ pointers. Typically, most open source libraries rely on this. But for a GPU, this isn't practical. So what we did in the paper was to introduce an indexed base polygon mesh representation that works as follows. So first, there's the vertex buffer that stores the 3D positions of the vertex points of the mesh. And then there's a half edge buffer that stores 6 integers per half edge. So in this particular asset, there's 12 half edges, and I'm storing 6 integers for each one of these. And these integer values actually store what would be returned by the operators I just described. So for instance, for this half edge here, this blue half edge here, which is indexed by number 1, so that's the first, that's element number 1 in the half edge buffer. The vertex ID here is number 2, so we have a 2 integer value 2. The twin is half edge 7, so we store 7 here. Next and previous is 2 and 0, so 2 and 0. The face ID is 0 here, and the edge ID is 4, which is edge number 4 here. Another property of our representation is that each half edge is stored in such a way that the face IDs are consecutive in memory. So here you have these 0s, 1 and 2s consecutively in memory. And what this is useful for is because if you're dealing with semi-regular meshes, so in the case where you have, say, quad-only meshes, which is what happens when you're dealing with Catmull-Clark subdivision, you don't actually have to store the next breadth faces in memory because you can compute them analytically. So in practice, what we do is we represent the control cage using this explicit half-edge buffer with 6 integer values. And when we subdivide the mesh, each subdivision level is represented using only 3 integers per half-edge. And so based on this representation, we derive some explicit formulas in our paper to implement this 1-to-4 mapping for the half edges. So with these operators at hand, we then derive 4 algorithms. These 4 algorithms allow us to evaluate a single Catmull-Clark refinement step entirely. And this is how it works. So it starts with a face point step that creates a vertex point for each face of the input mesh. So for this particular step, for instance, the vertex points are computed using a scattering approach where each half edge contributes to a single vertex point, and specifically the one whose face produces the vertex point. So for instance, this half edge here contributes to this vertex point, this half edge to this one, and this one to this one. Similarly, we have an edge step that creates a vertex point for each edge of the input mesh, and here again, each half edge contributes to the half edge it spans. A vertex point that creates a vertex point for each of those of the input mesh. So here, each half edge contributes to exactly 1 vertex point, and it's the one that is carrying, whose vertex is carried by the half edge. So for instance, this vertex point here is computed using this half edge that departs from it, this one, and this one. And finally, the topology step that computes a 1-to-4 mapping of the half edges to assemble these newly created vertex points into quads. And with these 4 algorithms at hand, we are able to evaluate the refinement step entirely. So a nice property is that each step consists actually of a for loop over all of the half edges. And for the vertex points, so the face, edge, and vertex points, we are simply scattering an information from half edges from the half edge buffer to the vertex buffer. So it turns out that this is really trivial to parallelize. So we discussed 2 implementations in our paper. We have an OpenGL-based one where we parallelize the for loop using a dispatch compute. So we wrote 4 compute shaders that are invoked using a dispatch compute over the half edges of the meshes. And we also wrote a CPU implementation that uses OpenMP and parallel 4 to over the half edges as well. And for these red areas, we simply need to have an atomic add operations, because since all the half edges are processed in parallel, they may access the vertex point memory concurrently. So the atomic instruction allows you to do that safely. And so with these implementations at hand, we started by benching the parallel performances of our algorithm. So we started with a single-threaded CPU and went all the way down to 8 threads on a thread rig per CPU. And we noticed that so the vertex point here is the grouped algorithm 1, 2, 3, and the half-edge refinement is this one. And so what we observed is that for both groups, we get perfect scalability, meaning that the performances increase linearly with respect to thread count. And then we benched also our GPU implementation, which obviously has more than 8 threads. And so here we also benefit from the parallel nature of our algorithm pretty evidently. So with this algorithm at hand, we benched our algorithm against OpenSubdiv. So first in the context of dynamic topology, which was the original motivation for this work. And so for this, we obtained very large speedups, as I mentioned in the introduction. And for static topology, again, we have more or less similar performances. We also benched our method against other open source libraries. So the reason why we did 2 groups is because most open source libraries don't support semi-sharp creases. So semi-sharp creases are these yellow edges here that allow an artist to control the sharpness of the edge of the subdivision surface. So for this batch of tests, we don't have semi-sharp creases actually, but we do have non-quad faces and boundaries. So in this particular configuration, we tested against OpenSubdiv, the method of Nice-Nernal, which is what OpenSubdiv builds upon, the method of Patney and colleagues, which only supports quads, so you only have these 2 bars here, and the method of Mlakar and colleagues, which is a very recent paper that was introduced a couple of months ago at Eurographics, and it does pretty much the same thing in ours. Actually, in practice, it outperforms us slightly most of the time. The difference between their approach and ours is that they rely on a more sophisticated mesh data structure, so specifically a sparse mesh matrix representation. So, I mean, it's essentially an alternative approach to ours, and it's up to the developers to choose which data structure best suits their needs. So yeah, the integrity of our benchmarks is available in supplemental materials. So we did exhaustive tests on a wide variety of subdivision depth and CPU thread counts. So if you're interested in this, I invite you to go and check them out. And one interesting thing I want to talk about here is that out of these exhaustive benchmarks, we realized that our algorithm was bottlenecked by memory bandwidth, and the way we discovered this is that at some point we tried to compute the vertex point in half precision, and this gave us a bunch of artifacts that you can see here, the obvious precision artifacts, so you can't really use it as extension, but it did give us a significant speedup ranging from 1.1 to 1.25 speedup in our test meshes. Obviously, the floating point can't be used, but maybe this is a discussion we have in the paper. Maybe it would be useful to have a GLSA extension that allows to compute normalized integer, 16-bit integers atomically, so we could actually store our vertex buffer at 16-bit precision rather than 32. So this concludes my talk. So hopefully you guys caught the main insight of our paper. We have these slight arrows that multiply by exactly 4 throughout the refinement of Catmull-Clark. This is always true even in the presence of non-quad faces. And the actual implementation is really simple, so it's available on my GitHub. It's really a few thousand lines of C code for the CPU implementation, and I think it's roughly 1,000 lines of GLSL code for the GLSL implementation. In future work, so one thing we looked into in this project was only uniform subdivision, and in this work in progress project I'm showing here, we are actually adaptively tessellating the subdivisions we've computed using our novel algorithm, which I just presented. Originally, Kenneth and I had this in an earlier submission, but we removed it because it was too exhaustive to talk about both the Halfedge insight and this specific algorithm. So we'll probably publish it at some point later this year. Another thing we'll look into is to generalize our Halfedge-based approach to other subdivision schemes. So Kenneth is looking into adapting loop subdivision using a Halfedge-based approach as well. This, with that said, this concludes my talk. If you have some questions, I'll be happy to answer them. Thank you. Can you hear me?
Yep, we can hear you. Thanks for the talk. I can see there's a question in the podium.
Can this be extended to be applied in mesh shaders? Good question. I don't know. So one of the advantages of mesh shaders is that they allow you to have these meshlets that would basically allow you to process complete portions of the, obviously the control cage, process them at once. I don't see how this could be efficiently used in conjunction with this, with our particular paper here. So it's an interesting avenue for future work. I don't know. I really don't know yet how I could leverage this efficiently right now.
Yeah, okay. I think, Ahmed, I guess you're next.
Hi, thank you for this excellent talk. So I think one of the important factors for performance on the GPU is memory locality.
Yes.
Can you tell us a little bit, of what have you seen when you do the subdivision and memory locality, and if it's one of the bottleneck for performance?
Yes, that's an excellent question. So yes, the bottleneck is definitely memory I/O. So one thing we could have done, but we didn't do it at all, was maybe to optimize the control cage. So sort of like recompute the index buffer so as to optimize cache locality. But we didn't do that at all. For the Halfedge buffer, there's really good locality because we have this 1-to-4 mapping, and so we're computing everything top to bottom, 1 to 4. So from one locality in memory, we write to 4 consecutive locations. So this is really compact. But one thing you could do is to optimize the locations of the twins, for instance. We didn't look into this at all, but this needs to be done rigorously. We didn't look into this at all.
Okay, I was really also intrigued by the adaptive snippets that you show at the end, and I was wondering how you do memory allocation, how do you allocate things beforehand when you don't know the depth of the subdivision you are going to have at the end?
So. So let's talk about something that's not published. Let's go. So it's based on my paper from last year, which relies on a binary tree. And for this representation requires you to allocate memory for the deepest case. So you always have memory allocated for as if you were going to tessellate the mesh at the deepest subdivision level, but you have a very compact representation. We're essentially storing 1 bit per triangle. So it remains compact, but you still have to allocate everything beforehand. I think you're probably aware of the fact that GPUs don't really like dynamic allocations. So so you have to really allocate everything beforehand.
Thank you, love it. Thank you so much.
You're welcome.
Can I go next?
Yep.
All right. So my question is, so excellent work. I really do like the idea of this Halfedge that it multiplies by 4. This is an astonishing observation.
Thank you.
Question is, you use atomic operations and floating point operations, and we know they're non-associative. Did you experience any numerical issues with that? So because some of the order of operations is important of the result with respect to the result that you get, but the scheduler of the GPU will reorder them, and that will cause you one frame, even though the input could be the exact same thing, could be different. Did you? This is the first question, and the question is, you said unorm, but couldn't you just use just regular integer adds? I mean, I guess essentially all you do is adds, right?
Yes, exactly.
So why didn't that work? I mean, or what? So this is the second question. So yeah, I'm curious.
So for the first question, so I may be saying something silly here, but as far as I know, floating point additions are commutative, aren't they?
They are, but they're non-associative.
Yes, but we are, the only thing we're doing atomically is our additions. So,
okay, but they're non-associative, I think. Maybe I'm mistaken too. Maybe we should dig into this later. Okay, maybe we can take this.
Yes. Okay.
I'm pretty sure the order matters for
the
order matters.
order you add.
Okay. So that's good to know. So in this case, we didn't notice anything. I mean, like in my demo, the demo I just showed, I'm recomputed everything. So every thread is, and there's no. So I guess if there were issues, you would see the vertices moving, right? You would see them.
Yeah, I would see them. Yeah.
Yeah, but I didn't notice this.
You could measure like the result and have like all your vertices spewed out to buffer, and then see if there's any numerical difference in it.
Okay. So I guess one thing I could do indeed would be to recompute the subdivision multiple times and compare the floating point value each time. I didn't do that at all. And I'm not quite sure I understood your second question.
The unorm thing. You were suggesting an atomic operation, but you could use integer if you just use adds, right? I mean, convert to float, but or maybe you would run the locking mechanism.
No. Okay. So the issue is that you need. So there is an atomic add instruction for integers, definitely. But what you need to do is to what you really want to do if you're representing a vertex buffer is you need to renormalize the coordinates afterwards, right?
Yes.
So if you're using the whole, since the bottleneck is memory IO, you want to use 16-bit integers. So one approach would be to do the whole additions first and then normalize after that. But if you're using 16-bit integers, there's a very good chance you'll overflow and completely destroy your vertices. So I mean, the idea would be, of course, to have a unorm, 16-bit unorm instruction in hardware. But I mean, I guess I'll have to do some lobbying at NVIDIA and AMD. But I mean, I think it could also be useful to compute like dynamic height fields as well, because I mean, if you have large terrains, you want 16-bit precision. But I mean, is it interesting? Is it interesting enough for hardware vendors to implement? I don't know. It's just a suggestion. Thank you.
Hi. So my actual question was already asked by Ahmed about the memory locality. And I just wanted to chip in next week on the SGP. I'm also working with high-performance geometry processing on a half-edge data structure. And I also have a very cheap update step, which means the locality was actually the issue, not the memory bandwidth. And I evaluated that using like a hierarchical clustering to reorder the indices. And I got in some cases over a factor of 5 improvement when the input was especially bad. So you may want to look into that because your update step is even simpler than mine. So I guess the actual fetching is really the bottleneck in your case.
Okay, thanks. Thank you for this information. I'll have a look into it. So the good thing is that it's I mean, you can reorder everything beforehand, right? So okay, I'll have a look into it. And did you use some?
There are a lot of methods.
Is it open source? Would it be easy for me to use?
I think it will be. So there is literature for that, and there are open source frameworks that do that. They're a bit slow, but you don't have to use a slow implementation.
Okay.
We can talk later about that if you're interested.
Do you plan to open source your algorithm?
Yes.
Okay. So I could use it.
Yeah.
True. Oh, sounds awesome. So when
you can already use it. We can talk later about that.
I'll check it out. Okay. Thank you. I'll definitely check it out. Thanks.
Thank you. you can talk later in the discussion room. There's a button for the discussion room to talk with the presenters later. So thanks again, Jonathan.
What should I do now? Sorry.
You can go to the discussion room.
Okay, thanks.
And before we start the next one, I'll remind everyone about the Best Paper Award, so don't forget to vote. But I'm going to remind you again after the talk. So for our next talk, the next paper is...
You'll need to continue in reminders.
Cooperative Profile Guided Optimizations by Mark Stephenson, Ram Rankin, and Stephen Keckler.
Hi, my name is Mark Stephenson, and I'm excited to present our work on cooperative profile guided optimization. This is a joint work with Ram Rangan and Steve Keckler, who are also at NVIDIA, and many other NVIDIAns contributed as well. Okay, so the motivation for this work is simple. Gamer appetite for performance continues to increase while Moore's law is slowing down. So this puts more focus on software optimizations to meet gamer performance demands. So we've seen several examples of exciting algorithm developments this week that are along those lines. This work focuses instead on improving the compiler for gaming workloads, which doesn't always bring the large gains were we to rewrite algorithms, but it does have the nice property that our work is generally agnostic to the algorithms. One question we asked early on in this project is whether we could use profile-guided optimization, which is a staple from the code generation literature, to improve gaming compilation. So don't worry if you're not aware of PGO, I'll describe it in this talk. So in trying to apply PGO, we discovered a lot of shortcomings for applying it to games. The novelty in our approach is overcoming these shortcomings. So the outline of the rest of the talk follows. First, we're going to introduce PGOs to the unacquainted. At a high level, PGOs leverage application profile information to make smarter compilation decisions. They're not new, they're a staple of the compiler literature, and they do work well. But in the course of this work, we did notice several shortcomings of PGOs for graphics applications that we'll describe. And all the shortcomings deal with the various difficulties in collecting the runtime profiles. So that led us to cooperative PGO as a potential solution to our profiling problems. As we'll describe, cooperative PGO crowdsources the profile collection problem. At the end of this talk, I hope I've convinced you that we should be using PGO for computer gaming, even despite all of its shortcomings and warts. But better yet, if we crowdsource the profiling problem, that can also overcome the shortcomings that we're going to describe. Okay, then now let me describe profile-guided optimization to the unacquainted. Okay, so the goal of PGO is to determine likely runtime behaviors of a program so that the compiler can make better compilation decisions. Without profile data, a compiler just has to guess about many runtime characteristics, such as how likely a branch is going to be taken, for example. Whereas traditionally a developer has done kind of once they have written their HLSL or the GLSL that the driver JIT compiles to run the game, PGO introduces additional build time complexity. So PGO is a three-step process. The first step here simply invokes the compiler in such a way that we instrument the shaders so that when the shaders run, we can collect runtime statistics. We'll briefly touch on some of the runtime characteristics that we might want to measure, but the most popular PGOs measure how important in terms of frequency of execution various regions of a program are. So a simple example is if we have an if-then-else statement, but the else path is never taken in practice, well, that's information that the compiler can leverage to generate more optimal code. So the second step here, though, is by far the hardest and trickiest part to pull off. The developer has to take the instrumented game and generate profiles that match what's expected to be seen in the wild. So this might involve playing a demo or maybe bribing some graduate students to play an instrumented game. But the quality of these profiles is analogous to the quality of a training set for machine learning workloads. So we really want to generate the right set of profiles. Then finally, in the third step, we invoke the compiler again, along with the HLSL that we started with, and the runtime profiles that we generated in step 2. And the compiler can use these profiles to make smarter compilation decisions. So take the if-then-else example again. What if we see that in a very register-hungry shader that the else path is never taken? Well, the compiler can simply spend time and resources making sure that the likely paths of execution are optimized at the expense of the cold paths. And at the end of this process, we have an optimized game. Okay, before I expose all the warts of PGO, I want to stress that they are proven. The idea is decades old, and some of the programs you run or apps that you use may have been optimized by PGO. So recent work has highlighted PGO success on web browsers, backend servers, and even graphics shaders. So I'm going to walk you through the idea using a PGO that we developed called PGZ that gets over 2x performance gains at the shader level. So here's the idea behind PGZ. And this PGO, by the way, was the genesis for this paper. There's a highly effective compiler optimization called constant propagation that finds provably constant code, constant expressions in the computation and propagates those constants forward. But what about likely constants? So these are variables such that the compiler can't prove are constant, can't divine or guess that they're constant in any way. For this, we really need a runtime profile that shows that at runtime, particular variables tend to be constant over the lifetime of the shader. So for instance, what if the compiler knew that R0 here is likely to be 0 at runtime? It could propagate that information forward. And side note, luckily, we can mostly ignore IEEE compliance here, such as nans and infinities, since most shaders explicitly don't require IEEE compliance. That means that R2 in this example is going to be 0 if R0 is 0, since 0 multiplied by anything is 0. Which also means we can ignore the computation in expensive work, provided there are no side effects there. We can propagate this forward, again, this R2, and we can notice that R3 is also 0, which means we don't have to compute more expensive work either. So this suggests a very simple transformation. A compiler can perform some estimation of the savings that could be attained if R0 is in fact 0, and create a fast path region and a slow fallback region as shown here on the right. So here, the compiler will insert a dynamic check because again, the compiler can't prove that R0 is going to be 0 dynamically. So it puts in this dynamic check. If it is 0, it short circuits the computation and we get very efficient code. Otherwise, we fall back to this path where we perform all of the original computation. So this PGO optimization is effective for some of the games we looked at, and we use it as a case study in this paper. Read this slide, please. The only point that I want to make is that there are really many PGOs that we can consider since PGO is a staple of compilation. This work isn't about any one particular PGO, though. It's about the infrastructure for enabling PGOs for interactive graphics apps. So I tried to convey that PGOs are good and that we should use them for games. But that said, let me talk about some of the pain points associated with PGO. So this graphic visually shows how PGO makes compilation more difficult. One step stretches out into 3 here. Without PGO, the developer is done here once the HLSL is written. But as I mentioned a few slides back, step 2 here is the nastiest step, and in my opinion, it really is the most error-prone step. We have to guess how the game is going to be played in the wild, and I'll return to that point in a minute. So when developing PGZ, it didn't take that long for us to realize that if the compiler changed too radically, all the profiles that we collected would be invalidated. We also had one example where we found a great PGZ opportunity in a game, but the developer patched the game and the opportunity went away. So finally, the driver can be patched, and it has a front-end compiler, and if it changes too much, that can also invalidate all the profiles. So given that the driver, the compiler, and the games are regularly changing, and collecting profiles is already hard enough, we may have to recollect these profiles every time one little aspect of the system changes. Okay, so I find this difficulty particularly amusing because I'm already a terrible gamer. So I think that most games are basically unplayable. But traditional PGO performs bulk profiling. You get all the profile information you need in one pass. Much of the prior art focuses on applications that aren't interactive. Even the ones that are interactive aren't really as demanding as gaming. So slowing Chrome down by, let's say, a factor of 1,000 to collect profiles would probably just take you back to the mid-90s or something. Try that with a game, though, and it's bad. We've run into TDR timeouts, and even when that doesn't happen, games just aren't playable with heavy profiling enabled. Another reason why profiling slows down graphics workloads significantly is because unlike most CPU workloads, bulk profiling on the GPU might have to operate on tens of thousands of parallel threads. I alluded to this difficulty when talking about the PGO flow, but gathering representative inputs can be really tricky. Let me show an experiment that I performed on the only game that I own, Hellblade. I modified the driver to dump the set of shaders that are used to render a particular scene, got to a point in the game, and simply looked in 3 different directions. And notice that while there's plenty of overlap between the various shaders invoked for each scene also does have unique requirements. And so we have to somehow make sure that we collect profiles for the shaders that matter. And that seems pretty hard to me, particularly on open world games where we have lots of degrees of freedom or can look in lots of different directions. All right, let's talk about cooperative PGO. Cooperative PGO is motivated by the following observations. The first one we've already gone over, and that's that profiling for PGOs is more difficult than we anticipated for games. But that's also because we were trying to collect all the profiles in bulk at once. But what if we took a piecemeal approach, and instead of collecting all the profile data in one go, we sample the profile information across time and space? So sampling, of course, will imply that we have to run the game multiple times, potentially on multiple machines, to get broad coverage. But consider for a moment that millions of gamers are playing the same small set of games on the same small set of consoles and hardware. Can we somehow leverage that fact and profile on the same machines that the gamers are gaming on while they're actually gaming? So that's what collaborative PGO is all about. And the statistics on Steam here are somewhat staggering. The top title often has nearly 1 million active gamers. The average number of gamers across the top 10 titles has upward of 50,000 active gamers. The top 2 games currently have over 300 million hours played. And the last point that I want to make is that, and this kind of ties into the fact that there's really a small set of games that everybody's playing. And that means that the shader compilers don't really have to be general purpose. We can cater compiler knobs, profiles, etc. to just those shaders that get executed a lot. All right, so this is the money slide that explains the whole thing. So let me make sure I cover everything. Here we show 3 of a presumably much larger set of collaborative compilation clients, collaborative PGO clients. The question we asked was, what if we could collect profile information while gamers were playing? Would that solve our profiling issues? So the objective is to make sure that gamers don't notice the profiling. No stutters, no slowdowns, and the key to that is super sparse sampling, having a huge gaming community, and also some reasonable engineering effort, which we describe in the paper. But here I want you to picture a cloud setup like GeForce Now or Stadia, or even a distributed infrastructure like GeForce Experience. But instead of doing bulk profiling, that is instrumenting every shader, every basic block, or every operand or whatever, we're going to perform sampled instrumentation. So on any given gameplay, we might only instrument a small subset of what needs to be measured for PGO. Most shaders won't be profiled at all, but instead we'll run the optimized shader. Most measurement characteristics won't be measured. As the driver performs draw and dispatch calls, it will flip a biased coin or roll dice as shown here to determine whether to instrument the associated pixel or compute shader. And at the shader level, more stochastic processes will determine what to measure during the draw or dispatch call. So at the end of gameplay, a collaborative PGO client will ship its piecemeal profiles to a central server that aggregates all the piecemeal profiles into a whole profile that can be used for PGO. And that's what we're calling a policy here. So each policy is game specific, and when a game resumes or starts up, the client can pull the latest PGO policy for the game and hopefully profit. So the grand vision would automate this entire cycle. And would this solve then our profiling woes? So let's go through the woes one by one. First, does this model complicate the build process? For sure, it absolutely does, but neither the developer nor the gamer sees any of that complexity. It's all kind of hidden in the secret sauce in the driver and in the aggregator. What if the compiler changes, the driver changes, or the game is patched? Well, we'll have to throw away all these profiles and start over and reprofile. But as we surmise in the paper, with a big enough gaming community, even with super sparse sampling, we could collect comprehensive profile information within minutes of the changes. 3, PGO profiling makes games unplayable. Well, as we'll soon show, piecemeal profiling can be performed with only minor overheads. Finally, 4, how do we decide what scenes to collect profiles of? Well, the beauty of this approach is that we don't have to. The gaming community decides what's important. And there's a caveat that I want to mention here. This work is research in progress. In the paper, as in the talk, we emulate the user community on a single machine. And at this point, our prototype is not production quality, so we can't just go deploy this thing on GeForce now. Before presenting some of our results, let me discuss our methodology. I already mentioned that we emulate a user community on a single machine. To make our experimentation more tractable and to allow deep dives for the PGOs, we also focus on single frames of games. So here's a subset of the game frames we look at. For Ashes of the Singularity, PUBG, and Serious Sam 4, we use the 3 frames shown here for each game to get a sense for the PGO's generalization performance. We also run the Metro Exodus demo. And so for the apps that we have single frames for, we tried to pick diverse frames. For these 2 PUBG frames, admittedly they look similar in this thumbnail, but apart from the character differences, one is 4K and the other is 1440p. So we run the frames over and over with piecemeal profiling enabled to collect the runtime profiles, and we aggregate the profiles into a coherent PGO dataset as described in the paper. We collected all the results with an RTX 2080 with the locked clocks. So in our paper, we discuss a hierarchical profiler. The first level of the hierarchy is a frame sampler that chooses windows of 1,000 frames in which to profile code. Outside this window, the overhead is essentially 0. The graph shows the overhead inside the window for a reasonable level of sparseness that we think could be deployed. Let's look at just the 1 in 1,000 case here. So the benchmarks are on the x-axis. The y-axis shows the overhead over the default driver that does not perform instrumentation. The bar for each benchmark, the yellow bar, shows the results if we only sample 1 out of 1,000 draw or dispatch calls. And for each instrumented shader, we're only going to measure 1 point in the space of things that we could measure. For example, a single 0 probability, so a single operand rather than all the operands in the shader. And notice that the highest overhead that we see is 1.5%, with an average overhead of 0.5%. And this is much, much lower than what we've seen in prior art. And it gives us some hope that we're not starting out at a huge deficit. So if PGO buys us back over 0.5%, it's going to be worth it. Okay, this is, I think, an interesting chart that shows how sample statistics converge to the ground truth. The graph you see on the left here is a control flow graph from a compute shader in Metro Exodus. So to the unacquainted, just think of a control flow graph as how the shader can branch during execution. For example, right here is, this is an if-then-else statement, this hammock right here. The last column, titled GT, is the ground truth execution of control flow paths in the shader, which we attain by full-blown profiling. The other columns show the results with sparse sampling on, where there's a 5% chance of sampling any given draw or dispatch call, and when we do, we measure 2 block frequencies. So from left to right, the frequencies converge to the ground truth. As we add more and more samples, we move left to right. After we've run the Metro Exodus demo 2492 times, we've amassed between 251 and 265 samples per block, and we're actually pretty close to the ground truth. I want to call out attention to this peculiarity of sample profiling, though. So notice the blocks L here and O should have the same frequencies, because whenever L executes, O should also execute. But because we're sampling, we see that these executions don't match perfectly in the sample profiling. They're pretty close, but they don't match. 1.95 instead of 1.98. So these minor mismatches are really unimportant for almost every PGO that we know of. For instance, the block frequency PGOs I mentioned earlier don't care precisely how hot or cold a particular block is. They just want to know whether a particular block is hot or cold. Let me now show the performance results for PGZ using piecemeal profiling. Note that our paper looks at 2 other PGOs complete with results, but in the essence of time, I'm skipping them. The game scenes here, again, are on the x-axis, and the y-axis is the percentage improvement over the default driver. And here we have 3 different frames from Ashes of the Singularity, PUBG, and Serious Sam 4. Also, for each game, we collect a profile specific to each scene. So P1 applies to Ashes 1, PUBG 1, and SS 1. P2 applies to Ashes 2, PUBG 2, SS 2, and so on and so forth. For example, let's look at PUBG 1 here in the middle. We collect profiles using only the PUBG 1 scene, and then we apply PGO using those profiles for PUBG 1. So when we do that, we collect profiles that are specific to a given game scene, then apply the PGO and run that specific game scene again. We're essentially creating a scene-specific compiler. So the black arrow for each one of these scenes shows the scene-specific compiler. And kind of as we'd expect, scene-specific compilers are generally the best performing. But what happens when we apply different scenes profiles to another scene? Again, here in the middle, when we use PUBG 3's profiles on PUBG 1, we get substantially less performance. And we see this in a lot of cases, in fact, in this chart. So the scene-specific shaders they're scene-specific. So note that we still generally do get some good performance increases using the other scene profiles. So let's look at the full graph, though, that we collected in the paper. So in addition to looking at profile sets created with just one scene, we can also combine them in various ways. For instance, the black bars show the results when we combine the profiles from scene 1 and scene 2 together. Most interesting on this graph, though, is the red bar, which is what we get when we combine all the profiles together into a giant profile. And the promising thing about this set of results is that the combined profile dataset performs near the peak for all of the benchmarks that we looked at. In addition, we do well on the Metro Exodus demo, which is comprised of thousands of frames. So we hope this bodes well for a collaborative PGO approach. All right, it's good to end on a hopeful note. PGO is a proven technology, and despite the difficulties we face collecting profiles for graphics workloads, it's a great tool for a developer to have in the toolbox. Collaborative PGO is not proven, but on paper it seems to solve our profile collection issues pretty well. And the preliminary results we've collected do look promising. So we're busy trying to make this a reality, but there's more to do. In the paper, we spend some time discussing some of the challenges we have to overcome before this does become a reality, including addressing privacy concerns and the potential for profiles from, let's say, day and night scenes canceling each other out. So we'd love to answer any of your questions. If you don't want to ask the question here, feel free to reach out to us at the addresses below. Thanks a lot.
So I can see we have a question here on the podium. Given the unpredictability of games, how do you handle black swan scenarios, especially when the average PGO can worsen them, potentially hurting the gameplay?
Yeah, that's, can you hear me, first of all?
Yep.
Okay, great. Yeah, that's an excellent question. And we haven't given it a great deal of thought for the general PGO. That said, in the paper, we look at something I think we call A to Z profiling, where we look at tweaking different compiler knobs and we time. We basically use timing information to go with the compiler knobs that give us the best performance. And in the paper, we optimize for average performance. We want to select the compiler knob that gives us the best average performance. But we could easily tweak that and kind of look at the tails of the distribution and optimize for minimum frame times, which might directly address this black swan scenario. But for the general PGO, we did look in the paper we called it profile dilution, where you do have a case where maybe you have a bunch of profiles that seem to suggest the game is being played in a particular way, but when you change the scenario, let's say switch from day to night, then suddenly those profiles don't really apply very well anymore. We've kind of benchmarked these cases, and we don't see slowdowns, which is the good news, but we lose all of our speed ups. But that's an excellent question. It's something we'll have to consider for future work.
So what are your thoughts about the cooperative PGO with varying hardware and varying patches? And are you still optimistic, or?
I am optimistic. That certainly would reduce the number of profiles that we have to work with, because we'd have to have a certain set of profiles for a given hardware, for a given console, let's say. But particularly if cloud gaming takes off, the the cloud platform has a lot of control over what the hardware is. And so, this kind of consolidated cloud infrastructure might actually make this idea easier to apply. Just a guess, but I'm hopeful.
Yeah,
so.
That makes sense. Go, Philip.
Hi. So this is maybe related a bit to the Black Swan scenario, but in general, PGO, it's already hard to find a good test run that is representative of your whole thing. And now you don't have any control over the players at all, so that might heavily screw the distribution in some way. Do you have any idea in how you can kind of solve that?
You mean it might steer the distribution? Well, so we're hoping it steers the distribution to what gamers actually care about. But yeah, I guess if you're talking about gamers who are kind of operating in the fringes of the distribution of how the game is played. But are you talking about being able to like quality check the run yourself on given frames that seem to be played a lot?
I mean, maybe more there are like typical scenes where a lot of players come together so that you get like 95% of your profiles from a particular configuration, and you don't even notice that your profiles are basically from the same scene, so it doesn't generalize as well anymore.
Oh, okay, right. See, yes, that could be an issue. I think the sort of numbers that we're thinking about, though, are more like, not 95 or 1,000 samples, but like millions and millions of samples, which hopefully gives us sufficient statistics to divine how the games are being played. But that's an excellent point.
I mean, maybe if you get some developer support, they can tag the scene so that it can be at least stratified by category or something.
Yes, that would be amazing, actually. In the paper, I think we briefly spent some time talking about our wish for some API level guidance from the developer to say, okay, we're switching scenes here. So then we can make kind of scene specific profile sets.
Yeah, cool. Yeah, thank you a lot.
Thank you.
Okay, I think we're a little bit over time here. So I suggest anybody who wants to ask more questions to head over to the discussion room, the presenter discussion room. There's a button on the screen here. And also I'd like to remind everybody to vote for the Best Paper Award, which thank Mark again, now that he's disappeared on us. Thank you for a great presentation. Thanks, Mark.
Thank you.
Yeah, don't forget to vote for Best Paper, and then we have the student competition coming up in about 10 minutes. Okay, thank you, everyone.
So hello and welcome everyone to this session for the student competition. I hope that you can see my screen in a second. There we go. And we are ready to start. Well, what is the student competition? It is actually the second time that this competition is held. And it's a competition that is open to any student, undergrad or graduate. So if you're watching at this moment and you're in the audience or maybe on YouTube or Twitch, don't hesitate to keep an eye out for the next competition and keep in mind that there's this option for you to participate. This year, we asked students to invite their work, to submit their work around a given theme. And because of the pandemic and all the bad things that are going on in the world, we said, okay, we want to do something different and asked as a topic for graphics for the greater good. And of course, this is extremely broad, but the idea was to either address a concrete real-world problem with the solution, or to provide a solution that is more general and indicates some usefulness beyond graphics. The evaluation of these projects were done based on novelty and impact. 2 top submissions were selected. The students got free registration to the conference, and the project descriptions will be made available on the HPG 21 website. They're already online, and you can also find this information here in OEA. If you look on the left sidebar, you can see the entries of the student competition here. But besides this, they also have an opportunity to present live at HPG. This year, of course, with the pandemic, things got a little bit different because we're in this online setting, but both of them submitted a video that we're going to watch. The winner of this project competition receives a cash prize of $750. The 2 entries that we're going to see a video about are efficient ray tracing for urban radiation source localization from Andrew Hollis and Ajinkya Gavane from North Carolina State University. And the second entry is MeshFrame, a lightweighted dynamic mesh processing framework from Chen at the University of Utah. With this, we're ready to roll the videos.
The loss or theft of radioactive nuclear materials poses a serious security threat, especially in urban environments where the large amount of critical infrastructure and dense population makes acts of negligence or terrorism involving nuclear materials particularly devastating. These concerns have motivated research in radioactive source localization in urban environments. Radioactive source localization is the application of mathematical and statistical model to estimate the location of radioactive source hidden in an urban environment. In our work, we estimate the location of a potentially threatening radioactive source, depicted by the red dot, using radiation data collected at several radiation detectors scattered throughout the city, depicted with blue diamonds. Source localization requires computing the average response at a detector given a source, which requires us to determine the intersection between the source detector rays and the urban environment. Here is the expression for computing the expected response derived from Boltzmann transport theory. While this approach is one of the most computationally efficient methods for computing the expected detector response, it can still be expensive when performing source localization in urban environment. For each pair of detector and source, we are required to compute the intersection between the buildings in the urban environment and the ray between the source and the detector. Computing this intersection can be challenging in a complex and urban environments with many buildings. To accelerate the computation of these intersections, we use NVIDIA Optics ray tracing engine. We load the urban scene with multiple city components into optics context. Following that, we compute a set of multiple rays using CUDA based on randomly generated location of source detector pairs. Finally, using the optics engine, these rays are then launched through the scene, and the building IDs of the hits are identified via the resulting hit locations. We compared the NVIDIA Optics implementation of the ray tracing method to a Python implementation that does not use the NVIDIA RTX GPU. We compared the performance of these two implementations by measuring the time required to compute the expected detector response for various sets of source detector pairs. We randomly generated 1,000 radiation source locations. For each of these sources, we computed the expected detector response for up to 100 randomly generated detector locations. We use NVIDIA Optics ray tracing engine to efficiently compute the intersections and demonstrate that it is as much as 1.6 times faster than alternative implementations. Our future work will focus on using the efficient ray tracing implementation as part of a larger radiation source localization framework. In particular, we are working on determining the optimal placement of radiation detectors to ensure we collect the most informative data on source location. The criteria we use to determine the value of detector placement require us to compute thousands of expected detector responses. Thus, having the optics implementation will allow us to quickly compute these criteria and efficiently determine the optimal placement of radiation detectors.
Thank you very much for this presentation. Let's give you a quick round of applause. And the second entry for today's competition, I repeat it once more, is MeshFrame, a lightweighted dynamic mesh processing framework. And the author is Chen from University of Utah. And we can also roll the video right away.
Hi, my name is Anka. I'm from the University of Utah. Today I will introduce a mesh processing framework that I developed, called MeshFrame. The purpose of MeshFrame is to make developing graphics application easier for everyone. A hard starting step of developing graphics application is to develop the code base. I still remember the hardships I've been through when I first started, but now there is MeshFrame. It's like an infrastructure of mesh processing. We have done all those painful and evolving works for you, and have all those modules developed, so you only have to work on those interesting parts. Here we illustrate the structure of the MeshFrame. MeshFrame supports both triangular and tetrahedral mesh, and its backbone is a half-edge, half-face data structure. All the elements in MeshFrame are managed by an efficient memory pool, which allows direct indexing, dense storage, and garbage collection. Except for the half-edge, half-face structure layer, all the accessing are unified with indexing. This is a great feature offered by the memory pool because it is very efficient and convenient. It also works great with the Python binding because Python really don't like pointers. Let's look into the implementation of memory pool. The memory pool allows us to semi-densely store all the elements together. By elements, I mean vertices, faces, edges, etc. The core structure of the memory pool is the vector contains pointer points to memory blocks, which actually stores the data. Each block packs up a certain number of elements so they can be stored together. The block is the minimum unit of memory application. This structure inherently assigns a unique index to each element and allows us to access, create, and delete an element in constant time. The memory pool also offers a built-in garbage collection mechanism. When an element is deleted, it will just be marked deleted and destructed, but we will keep its space and put its index to the recycle bin for future use. When creating new elements, we first look into the recycle bin, see if there is any reusable spaces. If there is, we will just reinitialize the space and use it as a new element. When creating a new element, if the recycle bin is empty, we will apply a space for a whole block. This ensures that all the newly created elements are still densely stored without breaking the pointers to previously created elements. This property does not hold for STT vector, which stores data in a single continuous memory block, because when pre-allocated memory is not enough for STT vector, it will release old memory block and rewrite the data to a newly applied bigger memory block, which will break all the old pointers. Our memory pool is very efficient. Basically, all the operations for it are constant time operations. We also found out that the semi-dense storage structure and directly indexing is actually preferred over pointers by modern CPUs, because it allows CPU to more easily predict and catch a memory usage. MeshFrame supports both static and dynamic properties. Static property is just a member added to a class. In comparison, the dynamic property is much more flexible and convenient because it can be added, removed in the runtime without the intervention of compilers. Here we compare the speed of our dynamic property with static property and OpenMesh's dynamic property implementation. You can see, while being more flexible, our dynamic property is almost as fast as the static property, much faster than the OpenMesh's implementation. Dynamic mesh editing, while maintaining the Halfedge structure, is very complicated because the interconnection of vertices, edges, faces, and half-faces. It's like a spider net. The code of doing this is very involving and requires a careful work, but luckily we have implemented for you, so you don't have to. Our implementation of mesh structure editing is also very efficient, faster than MeshLab's implementation. The dynamic property of MeshFrame is ideal for Python binding. Here is an example of computing vertex normals through Python binding. The vertex normal is stored in a dynamic property. The Python binding really opens an easy way for those who want to get into mesh processing. And that's all I want to talk about today. Thank you. Bye-bye.
Yeah, thank you very much for this nice presentation. Actually, thank you to both speakers. And now I know a lot of you already expected I'm going to say, and the winner is, but the winner is going to be revealed at the closing session, so we're not going to announce it here. Instead, we're slowly moving over to the keynote session that is about to start. But before we do this, I still wanted to remind you that there's still the button to vote for the Best Paper Award this year. And if you haven't done so, then please go ahead and click the button now in order to make your choice. In order to facilitate this task a little bit, we're going to take a look at the video sequence of the overview of the papers one more time. Very good. So please vote now. The poll is still open for the next few minutes and will close during the session so that we can count the votes and then come to a conclusion on the Best Paper Award. With this, I welcome you now to the keynote session that we are about to start, and you probably have been waiting for already for a few minutes. So I have the great pleasure to introduce to you Karan Singh. He's a professor at the of computer science at the University of Toronto, and he co-directs a globally reputed graphics lab and HCI lab, GGB. He has over 100 peer-reviewed publications and has supervised over 40 master students and PhD students. His research interests lie in interactive graphics, spanning art and visual perception, geometric design, fabrication, character animation, anatomy, and interaction techniques for mobile and augmented virtual reality. He has been a technical lead for the Oscar-winning software Maya and was the R&D director for the 2004 Oscar-winning animated short Ryan. He has co-founded multiple companies, including Ancestra Architectural Design, Yali for face animation, and Janus VR, a virtual reality application. In his talk, he will describe the fundamental need for creative visual communication. Karan has quite a broad range of interests, as I've explained before, and worked on many different topics, which will also become apparent in his presentation, which will cover art, mathematics, interaction, and AI. We also reserve time at the end to look at some of the open challenges around the perception of shape, color, and animation, and this will be initiated with several examples for creative interfaces that will be presented throughout the talk. Hereby, he will explain how problems should be addressed in sketching, color modeling, AR, VR creation, and facial animation, and we can then discuss these topics with him afterwards. With this, I'm very much looking forward to the presentation and the following discussion. Thank you.
Hi, my name is Karan Singh, and I'm a professor in computer science at the University of Toronto. It is a pleasure to be here today and talk to you about creative visual communication. My work in interactive computer graphics often relies on efficient interpolation, surface and volume optimization, and real-time performance for interactivity. So I hope that this talk will inspire future work in the context of high-performance graphics. Let's start with communication, which the dictionary defines as the exchange of information or ideas, something I'm doing by talking to you right now. Computer graphics realized that a picture is worth 1,000 words a long time ago. I want you to listen to this carefully.
John, we're going to show you a man actually talking to a computer in a way far different than it's ever been possible to do before.
Surely not with his voice.
No, he's going to be talking graphically. He's going to be drawing, and the computer is going to understand his drawings. And the man will be using a language, a graphical language that we call Sketchpad.
You just heard computer graphics pioneer Stephen Coons communicating Ivan Sutherland's seminal drawing system, Sketchpad, from 1963. 50 years ago, it was mind-blowingly unthinkable to talk to a computer, but drawing, maybe that was possible. Today, speech synthesis and recognition are both largely solved, but visual communication is still an important area of research. Why is that? Think of a human as a device. We have an audio in, we have an audio out, a video in, no video out, no magic rays of light projecting out of our brain. So now, when Salvador here has a creative idea, he talks graphically. And when humans or computers understand his drawings, that is creative visual communication. Let us explore this video in and out. We understand what we see using a mix of perceptual cues or rules and a memory of what we have already seen. So these impossible Penrose triangle sculptures seem to work from these viewpoints because 1, we expect lines in 2D to remain lines in 3D, and 2, we expect things that are close in 2D to remain close in 3D. Similarly, the imagined 3D object here is entirely based on a visual memory. There are some great insights on visual rules in memory when we look at sketching and sculpting as proxies for a video out. In Betty Edwards' book, Drawing on the Right Side of the Brain, she says most children have a passion for drawing that they lose as they get older. She attributes this to a shift from drawing what you see or visual rules to drawing what you know or visual memory. Regardless, we all mold, gesture, and doodle. And that is the path we are going to take to Espresso Man here, a modern incarnation of the Utah teapot. Along the way, you will come across various stages of communication and a mix of 2D and 3D sketching and sculpting techniques. Let's start with ideation. Ideation is self-communication. My 6-year-old daughter had to explain to me that this was supposed to be John Lennon in the Yellow Submarine. I then asked her what this was. She had no idea because she didn't draw it. Frank Gehry did. Ideation sketches are rough, and in the early stages of a design, designers explore an ideation space through many quick 2D sketches. Sketch Soup is a system we built to aid 2D ideation. Once we have a few sketches, like these irons, we're able to automatically find matching features and embed these drawings in a design interpolation space that the user can interactively explore. When they find a design they like, they print it, oversketch to refine it, and feed it back into the design space. Technically, the challenges to overcome are feature matching with sparse, noisy input and interpolating missing or additional parts in a partial design space. Ideation in general is real-time exploration of an unbounded visual design space, and thus can benefit greatly from high-performance graphics techniques. Given these 2D curve sketches, we now want to algorithmically reconstruct a 3D model. But not just any model. We want to recreate the model that humans perceive, which we assume is the same model that the artist intended to communicate. The answer to this lies in art and design books that teach artists what descriptive curves to draw and why. Our job was to reformulate that artistic intuition mathematically. For example, when we see two smooth 2D curves cross each other, we tend to perceive them as crossing orthogonally in 3D. Here's a teaser video explaining the idea behind True to Form.
True to Form is a conceptual modeling tool that applies design and perception principles to lift 2D sketches off the page into user-intended 3D shapes. We exploit descriptive curves that designers strategically sketch to convey 3D information. Selectively detecting the right set of sketch properties to enforce is what makes our approach click.
In the digital world, though, we are not stuck drawing from a single viewpoint. In fact, we can interactively draw strokes and change views as we build the 3D model. Now you just saw the user draw 2 strokes there that we would like to lift out of the page into 3D. The trick to use here is the knowledge that they are a symmetric pair of strokes. Mathematically, that is the same as drawing the same stroke from 2 views, this one and the view reflected in the plane of symmetry. And that is all we need to triangulate the curve into 3D. Around this time, we realized, okay, we can certainly draw 3-dimensional curves by 2-dimensional sketching. But are these curves we create exactly the curves we imagine in our head? We give a few simple curve drawing tasks to both lay users and professional artists. It turned out that all users showed inaccuracies, and interestingly, everybody made similar mistakes. So please read the paper if you are ever feeling bad about your artistic skills. And here is a little test. Which of A or B is closer to the projection of a cube? Most people tend to pick B. And B is in fact the default PowerPoint glyph for a cube. But it is also 40% deeper than a cube, the precise projection of which is shown here as A. So humans have a video in, but one that is subject to systematic bias. One of the artists actually did very well on our tasks like draw a circle half the size inside the square, or the middle cross-section of this cylinder. Her work had some lines that looked different though from the curves we just saw. These lines are part of a system of analytic drawing that define a scaffold within which to situate your sketch. Digging deeper, this is the definitive text on analytic drawing by Chen. But a much cooler text on analytic drawing is How to Draw Cars the Hot Wheels Way by Scott Robertson. In this case, the scaffold provides the constraints on how to interpret 2D strokes as 3D curves. You might think it is overkill to spend all this time building a simple cube here, but complex 3D curves are built using the same drawing interface, using the same concept of a scaffold. As we see here, curves and scaffold lines are dealt with homogeneously using the same drawing interface and a probabilistic inference that lifts the 2D drawings into 3 dimensions. As a final example on sketching, Second Skin looks at using existing 3D geometry to situate a sketch. A common designer workflow is to use renderings of 3D objects as a visual reference on and around which to draw. We find that these strokes can be classified into a small number of types that makes their 3D reconstruction on multiple layers easy. Here's a short clip of Second Skin in action. These techniques all generate a network of 3D curves. To create a surface 3D model, we need to solve two further problems. First, we need to figure out which cycles among the exponential number of cycles in the graph of 3D curves correspond to surface patches. And then once we know which cycles to patch, how do we patch them? As you can see, some cycles can have quite a complex and sometimes ambiguous shape, and a mix of geometry, topology, and user interaction is needed to solve the problem. To recap, we have just seen four very different approaches to lifting 2D strokes into 3D, each with its own perceptual trick to escape flatland. It is also worth asking, what if the curve escaping flatland is in fact flat? Planar curves are after all common in design and fabrication, and FlatFab is a system that is able to exploit this planarity to ease the creation of planar curve assemblies in 3D. As we see here, FlatFab is an end-to-end solution with a fluid interface to create physically stable planar section assemblies. While most current devices, both input and output, are indeed flat, one might think that the arrival of immersive display and input might completely disrupt sketching for creative communication. It turns out, though, that while drawing in space has the appeal of a magic wand, the absence of constraints and a haptic surface to draw on make even simple design sketching challenging. CASI is an immersive sketching system that addresses this lack of constraints by inferring these for freehand 3D drawings to create a neatened curve network and predicted surface patches. Drawing curves on surfaces is almost as important as drawing in midair for 3D visual communication. In 2D, there is a simple what you see is what you get answer to this problem. That is, you project your 2D stroke along your viewing direction from the screen onto the visible 3D surface. In 3D, you would think this is easier because you can reach inside the screen with your controller and draw exactly on the surface. Turns out that without a physical 3D surface to push back, it is almost impossible to draw on a surface. So now what seemed like an easier projection problem just got ambiguous and harder. What we're looking for is a real-time projection of a drawn 3D stroke P to a stroke Q that lies on a given 3D surface. As a user, we have some expectations of what Q should look like. Unfortunately, context-free approaches in current use, like closest point snapping or graffiti spray can technique, often fall short of user expectations. We noticed in our pilot testing that a key difference between 2D and 3D drawing is that while users may not be able to draw directly on a surface, they tend to draw P to mimic their expected shape of Q. In its crudest form, this means that your next local step along Q should be similar to the step along P. This caused a bit of a flashback to 2004 when we looked at a similar problem to geometrically wrap hair-like appendages with complete artistic control for an animated film called Ryan. Here's a clip of that in action.
Christopher.
In the case of chords, we shoot a ray from the current Q through P and project the next Q by growing the chord along the ray or grazing scene intersection based on the chord stiffness. In our VR context, we transport the segment on P to Q and then project by computing a smooth closest point. This allowed us to design an effective anchored closest point technique where the user's stroke is transported to the object and then projected to a smooth closest point. We tested this mimicry projection comprehensively with 20 users in VR, and it works great. Now, Cassie and mimicry address the greater need for constraints in XR. Symbiosis Sketch is an example of a hybrid interface that uses 3D drawing in AR for creating 3D surface canvases that are then refined and detailed by drawing on a 2D tablet. Hybrid interfaces are also key to mixed media communication. Here's a traditional artist storyboarding in 2D on a tablet who can collaborate in real time with a director to plan and view a film in VR. Further, there's a rich interaction space between high degree of freedom hand gestures and immersive creation, such as controlling the physical simulations you see here. Another metaphor for creative visual communication is that of sculpting. And here you see our work on MeshMixer, an approach to clay-inspired drag and drop 3D model editing. We solved this problem by embedding the boundary of the dragged region in a dynamic local parameterization of the dropped region, and then drop and stitch the interior as a curvature-aware deformed mesh. Over the years, MeshMixer has become a powerful model creation and preparation tool to support 3D printing and prototyping. Another aspect of 3D sculpting is the ability to control the evolution of lower degree of freedom structures, such as seen here on an open source sculpting system, Neo-Baroque. Finally, there's a rich body of problems in artistic representation, creation, and editing of color for creative visual communication. Here we see the real-time exploration of color gradients for design applications using color triads. Unlike most bicolor gradient interfaces, the modeling of specular objects teaches us that we likely need at least 3 colors to capture ambient, diffuse, and specular components in natural images. To summarize here, tools for creative visual communication turn artistic practice into interactive tools that exploit mathematical terms that can be optimized and perceptually validated. A similar approach can be applied to multisensory creative visual communication. For example, to turn a vocal performance into a visual performance. About 5 years back, we were able to resurrect the 30-year-old problem of lip synchronization based on a simple observation. A traditional animation of human speech is based on a one-to-one mapping from phonemes to visemes, that is the appearance of the face for that phoneme. And this is a phonetic sheet from the animator Preston Blair dating back to 1948. Now imagine the phonetic sheet for a ventriloquist. It's this single image. In reality, the mapping of phonemes to visemes is at least one-to-many, and we were able to capture this variation using a combination of jaw and lip contribution to the sound produced. As you will see here, same words, different performance. Same phonemes, different visemes.
Jack and Jill went up the hill. 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 Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after.
And here are some results showing expressive variation in speech.
You're an internationally acclaimed composer who's traveled the world enjoying one success after another, and I am an out-of-work tire salesman, so I guess that's not surprising. But, you know, I hope you take a minute out of your busy schedule to listen to this tape, which you just opened up in the mail. If you can't listen to it now, maybe you can listen to it tonight. Tonight. Huh. I love that song. What a melody, right? And what a sentiment. I mean, tonight, I'll meet my love tonight. Where is she, Lenny? Give me a hint.
For real-time applications, we are able to use a 3-stage network to learn these viseme mappings, as well as the jaw and lip activations used to produce Jolly's speech. Here's a short teaser of this.
We present VisemeNet, a novel deep learning-based approach that is able to produce animator-centric speech motion cues and automatically derive modern production phrase rigs directly from input audio alone.
我们提出一种基于深度学习的方法 VisemeNet。该方法能够生成面向动画师的语音运动曲线。
While VisemeNet pushes towards real-time visual speech, co-articulation remains a grand challenge. Here we see heavy co-articulation of the T, E, and R in water. Co-articulation, however, is based not only on what has been said, but on what is about to be said. For example, the mouth shape is different for F, depending on whether we say feed or food. In keeping with the theme of this talk, Jolly is an animator's tool, producing sparse, compact, editable curves as opposed to the use it or lose it nature of performance capture. And last year, we were excited to see the release of Cyberpunk 2077 with our lip sync technology Jolly driving the facial animation of 50 hours of gameplay in 10 languages.
We'll kick off with Judy. She's more of a calm speaker.
Slow, deep breaths. Your cortisol and adrenaline spiked, but the soft activated your hormone blockers. Nothing happened. You're alive and well.
Next is Dex, who is a little bit more energetic and mysterious.
Apparently, first thing to burst are the eyeballs. Get a nice clear pop. Then the rest goes goulash.
And finally is Placide, who has a vibe of a dangerous cyberpunk hacker.
10 network scum dead. The grid, BBS is destroyed. But you walk, you breathe. How?
These animations, labeled as a benchmark by CD Projekt Red, are in fact completely automatic, audio-driven Jolly animations. And here is a clip describing the importance of a multilingual vocal performance, not just to the lips, but the whole face.
First, English.
Slow, deep breaths. Your cortisol.
I'm stopping on the word cortisol. Judy is stressing this word and her eyebrows furrow slightly right on that word. Now, French.
Doucement, respire à fond. T'as eu un pic de cortisol et d'adrénaline. Doucement, respire à fond.
Stopping on the word fond. It's a different part of the sentence than the English version, but again her brows are following her inflections perfectly. Now German.
Tief durchatmen. Deine Cortisol- und Adrenalinwerte sind angestiegen, aber die Hormonblocker wurden aktiviert. Du bist gesund und munter. Tief durchatmen.
Stopping on the word atmet. German is a highly inflective language and her brows respond strongly to that word. Now Japanese.
大丈夫。コルチゾールとアドレナリンが急上昇したけど、ホルモンブロッカーが効いてくれた。あなたの体は何ともないよ。
Japanese is not an inflective language, and Jolly responds by moving her brows in only minimal motions.
In general, the face as an instrument of communication is incredibly complex and high-dimensional. There is a rich set of problems to be solved in the real-time artistic sampling and exploration of this high-dimensional space. Here we see an approach to learning a subspace or manifold of plausible facial expressions that can constrain the interactive exploration of faces. Or reducing a continuous face animation into a small set of representative expressions for 3D printed stop motion animation that can reduce printing time and material by many orders of magnitude.
Hello. I know you're expecting to see our film now. Well, there's been a slight problem.
Finally, here's a glimpse at some upcoming work. Artists tediously handcraft layouts of hundreds of facial controls for interactive manipulation, as seen here. A UI layout on a face can be formalized as a mapping of UI elements representing control parameters C to face vertices V. More importantly now, we need to describe what we mean by an optimal layout. Producing such UI layouts automatically requires understanding the insights artists use in placing controls. For example, placing control UI near regions of the face that are maximally deformed by the control, or minimizing spatial overlap between UI controls, or minimizing UI model occlusion, or respecting symmetry in facial deformations, etc. Current high-end faces can have over 100,000 vertices and hundreds of controls. We reduce the layout mapping complexity by pruning static, hidden, or undesirable mesh vertices, then grouping controls of similar regional influence, and further clustering these controls based on their spatial independence. Finally, we can use a downsampled vertex set as input to the exponential stage of our algorithm that uses integer quadratic programming to optimize the design objectives in mapping controls to vertices. Optimizing these objectives mathematically produce layouts that match user expectations and enable a homogeneous interface where the face can be controlled interchangeably by the user interface or by direct manipulation of the face, as seen here. In summary, there is centuries of experience in visual communication captured by artistic practice that computer graphics can continue to leverage. And the creation of tools for creative visual communication will remain a fertile area of research, at least until we are able to develop an explicit video out.
So what do you want? Supercar? Big house? You want to rule this city? Well, you ain't getting anywhere without an upgrade.
I leave you with one final thought. Upgraded tools provide upgraded communication. They do not in themselves produce better or upgraded creativity. The ideas are all in our heads. Better tools just make it easier to get them out. Thank you.
So thank you very much for this really inspiring talk with a lot of interesting directions. I hope that Karan is here and can join me on the podium. But we might be unlucky. Probably it's due to a technical problem, then I would have to apologize.
There I am. I was just trying
there
to.
You are.
Sorry about that. I was like, no, don't go away. I'm here. I'm just.
I was already half in panic.
Yeah, I'm just trying to figure out how to get how to get onto the screen. There we go.
But it's nice that you
All
made
right.
it. Very good. Yeah, thank you very much
Yes.
for this really nice talk. I mean, it's so many topics that you worked on. There's a lot to discuss and a lot to investigate. One thing that I was actually wondering about, and I mean, you took this already a little bit up in your talk, was we have a lot of interaction now in 3D because of VR and AR and so forth. But for example, in the visualization community, they usually go back to 2D because it's just so much more intuitive to work there. Where do you see this development is going to go? Do we miss the right devices? For example, we need more haptic feedback. Do we need even better algorithms? Or is it not a competition and depending on the task, we will have different tools that we work with?
I think the answer is a bit of both. Definitely, there is a task-specific aspect to the use of dimensionality, and one of the things that we found, in fact, is really interesting. In the talk itself, you may have noticed, I started out by talking about sketching, and that sketching inherently is this two-dimensional activity that you do, and then the big problem becomes how you lift it into 3 dimensions to really bring the item that you wish to communicate across to the other person. And so we were fighting this journey from 2D to 3D, and then one felt, well, if you go into the domain of sculpting and the kinds of things that people do with clay and work with sculpting, that this would be much more straightforward. But one of the things that we realized is that if you're working with sculpting, but at the same time, you're not actually working with your hands and you're still working with two-dimensional interfaces like a pen and tablet to perform this kind of sculpting behavior, then again, you get into this interesting dichotomy between dimensions. And that's from a user standpoint. what we find that's equally interesting is from a technical standpoint, when we go to solve these actual problems of how, for example, you can take that face and pull it off one piece of geometry and then drag it around and put it onto another piece of geometry. Even there, we find this interplay between dimensions, because we found that the best way, or the way that people are thinking about the problem without consciously thinking about it, is that they have transformed this 3 dimensions into 2 dimensions, because they have taken their geometry, which is in 3D, but now they are thinking about it as a 2-dimensional problem of dragging it around on a manifold, on a surface that is 2-dimensional in topology, that they just happens to be embedded in 3D. So there's a wonderful example of us going down from from 3 dimensions into 2 dimensions. And one thing that I didn't get into was when we talk about this mid-air drawing and mid-air projection in 3 dimensions. One of the problems that we found, so we came up with a simple technique that actually works incredibly well, where points are projected, then anchored and projected and anchored, projected, and trying to do this mimicry. What we found was that the closest point projection, as we might expect for a mesh, is not continuous. If you have a continuous surface, closest point, at least locally, tends to give you nice continuous projections. But for a mesh that has edges and vertices, it kind of sticks at the vertices. And there was an example where we borrowed from some other research, in particular a paper called Phong projection, that allows you to smoothly define functions on a discrete surface. And we took this into space. So we solved this for a volumetric situation by going from 3 dimensions into, I believe it was an 8-dimensional space, where we could kind of unfold the these discontinuities on the mesh, and then project there. So I think the answer is yes. As new devices come around, working with a number of different devices, they have their own eccentricities. And so really, as far as communication is concerned, or creative communication, the summary answer is that you really have to look at the task. And there is some dimensionality that works really well for it. As you mentioned, for a lot of visualization tasks, a flat format is in fact better. And having the charm of things spinning around in 3D actually is just a distraction in those situations.
Absolutely. Thank you. If people from the audience have questions, don't hesitate to step up to the mic. There's a button here, or otherwise you can also post your question. But let me then continue with another question for you. I was actually wondering, I was recently in a panel when the discussion came up whether we are losing more and more of our expressivity because our tools get better. So if you look at 3D movies, for example, there is a certain style that is now established, and it doesn't matter from which company it comes, there is some resemblance there, right? Do you think, and I mean, your last slide is alluding a little bit in this direction, that we need new tools, different tools, or do we have to make things harder again to boost creativity?
That's a fabulous question, and in fact, it's one I haven't spoken much about my work over here these days at Weta, but in general, philosophically, that is a question that the artists seem to have quite often with us every day, particularly with the onset of data-driven techniques. So better tools, yes, but also tools that very strongly rely on previously created content. And so that previously created content is constantly pulling the artist towards that style, towards that space. And yes, at the moment we are seeing the kind of, I would say, the fight between extrapolation, which is perhaps going towards a new style, and interpolation, which is what I won't say all, but a majority of data-driven techniques are kind of giving that to you. We found this actually. I showed a very short clip where we used a manifold, a face manifold, to kind of keep within what is considered a meaningful subspace of realistic or plausible expression. Well, what we didn't say was the way we defined plausible was, or realistic, was by taking footage from about 15 minutes of an animated film. So as you put it exactly, now the artist is constrained, if they use this system with the manifold, to produce things that are in the style of that 15-minute film. And the way we tried to go away from that a little bit is that we allowed exploration. There was a refinement stage. So there's an exploration stage where you're forced to stay within that style and domain that you were working with. But then there was a refinement stage where you can say, okay, I'd like to escape this manifold. Maybe I won't go too far. So it's almost like you let the artist out on a leash and let them explore a little bit of the region, of this very high dimensional region in that area. And so that's one way of fighting this. So again, somewhat of a longish answer, but I don't believe that the tools are necessarily making people less expressive. What they are doing is they're trying to push people towards working in a particular way or working in a particular style, and that makes it harder for them to break away from. And it is important that tools actually allow that. They have that, what we call a high ceiling for creativity, that allows them to break away when they need to.
Yeah, you mentioned also this technique for the mouth animation, and what was really striking to me was this difference between different languages and how that also has effect on the facial expressions that we have. And nowadays, you see all these developments in VR, for example, that people have these virtual avatars. And you can imagine that in the future, if you're in contact with somebody via VR, you would even translate the language on the fly and then have the expressions match these languages. I was wondering, is this going to affect also the communication in some way? Because we will not recognize the reaction of the speaker themselves anymore?
Yeah, I think there certainly is some of that. One of the things that we saw in that short clip was, and this was one of the things that CDPR was very keen on, is that breaking from that traditional idea that lip sync or language localization, dubbing, which is the word used, kind of stops here around this region, of the lips and the mouth, and in fact is very, very strongly connected to everything, to the rest of the face, but not just the face. In fact, one of the things that we animated that our model animated for Cyberpunk was also the neck. And our neck motions are also tied to speech inflections and the kinds of things that we do. And yes, at some point, if language gets replaced, and then people's gestures and their reactions, and we all have different ways of speaking. Some of us may move our neck around more, move our head around more, some move less. One of the things that we're very excited about wanting to get into, at least I am personally, is hands. Not hands in general for animation, but hands in particular in their connection speech. If you're Italian, you use these almost as much as you use the region around your mouth. So if you replace all of that, yes, then we do run the risk of having avatars that are completely unrecognizable from the original person, which in some ways I think has already happened when you take these very wooden avatars and you combine them with TTS or text to speech, where you're typing things in and there's this robotic voice that's enunciating it for you in VR.
Yeah, or the very abstract icons that we can use here. But
that's
we
right.
All those from the audience. Please
Excellent.
go ahead.
Hi. Yeah,
Hi.
so basically continuing a bit with that data-driven tools tend to interpolate and maybe stifle creativity a bit. I was thinking that in the procedure generation community, you have this paradigm that you want to do programs that do automatic variation for you. So you provide some kind of input and then it helps you with exploration. Did you experiment or have an opinion about kind of these tools?
Yeah, absolutely. I think, and you're right that this is something that's a little driven more from the procedural community, but having worked on both sides, so Jolly by itself is not entirely. It's kind of a mixed, hybrid tool. It has a data-driven aspect that works with language models and data to deal with alignment and certain aspects of the lip sync process, and then the actual curve generation, which is very sparse and compact, is procedural. And you're absolutely right that that regardless of whether your technique is data driven or it is procedurally generated, this ability to kind of explore the neighborhood of usually these very high dimensional techniques is quite beneficial. I mean, I think this becomes that for me there are two grand challenges in that exploration space, one of which actually is a grand challenge for this community, which is the space is very large and you need to be able to simulate samples and render samples of the neighborhood of where you want to explore very quickly if you want to then present it to the user, for real-time interaction, which becomes the second grand challenge, which is for the HCI community, how you then present that high-dimensional data in a manner that is easy to navigate and quick to navigate. So I think it's a fascinating area. It's a great area, and one that I am actually actively working in a little bit. Again, that face manifold paper was one example actually of this kind of exploration work.
Yeah, really cool. I saw that a lot for texture synthesis, but for face and animations, I would guess it's also really great. Thank you.
Yeah, thank you very much for this excellent question. We're running already out of time because the closing session is coming up. I hope, Karan, that you will stick around a little bit in the virtual space afterwards. We also have the OEA party, which is basically a social mixer where people can get together and continue this really exciting discussion. Thank you again for this fantastic talk. And
thank you for the opportunity.
Round of applause.
Thank you.
All right. Well,
want to thank everyone for attending HPG this year. It's been an amazing conference, and I know I've gotten a lot out of it, and I really do hope that you do as well. We have some important closing remarks for you as we wrap up this conference. And then after this session, there's going to be a social time in the various social rooms. And I really do encourage the premium registrants to meet there and mingle and discuss what we've seen and so forth. Another quick note, if you go to the program page of the conference, there will be links to papers, the student competition entries, and most of the videos. So those the papers are already on there as links to the digital library. The videos, if you go to each day's YouTube stream, you can already get at it. The descriptions on YouTube have the timestamps. We'll make this a little more directly usable in the next couple days. Also, please know that the papers are going to be freely available. The conference was able this year to pay the open access fees, and so they're going to be available indefinitely. And that brings us to one of the more exciting parts of our closing each year.
Exactly. So let's start with this year's Wolfgang Strasser Best Paper Award, worth $1,000. The results were extremely close, and therefore we have a tie for the second place. Runners-up on the shared second place, we have a half-edge refinement rule for parallel Catmull-Clark subdivision by Jonathan Dupuy and Kenneth van Hoyt. Congratulations. Also on the second place, we have hardware adaptive high-order interpolation for real-time graphics by Daki Lin, Larry Seiler, and Chen. Congratulations. Let's give them 2 rounds of applause. And the winner of the HPG 2021 Best Paper Award is Vertex Blend Attribute Compression by Bastian Kut and Kieran Myers. Kieran Myers, congratulations. Then, for the HPG 2021 Test of Time Awards, we decided to delay this one until next year. Why? Because then we are able to reach the 10-year latency. Before we had 9 years, and now we're going for 10 years.
All right, thank you very much. The fun keeps on going.
Hi, this is Jose, the poster chair. We have a Best Poster Award. The cash prize is $500 US. And so the Best Poster Award goes to Opportunities to Avoid Texture Lookups in Modern Game Frames by Aditya Ukarande, Deep Shekhar, and Ram Rangan. Thank you. Congratulations.
So next up is then the Student Competition Award. This is a prize money of $750 that will be handed out to Efficient Ray Tracing for Urban Radiation Source Localization, Andrew Hollis and Ajinkya, Gavane. Congratulations. All right. Well, a big congratulations to all of our winners from the committee and the community as a whole. And on that note, I would like to take this opportunity to really thank the entire committee for all of their work over the last year to make this conference possible. We had another year of doing it virtual, and I feel that we have succeeded in making this virtual conference have a more integrated sense of belonging and community. And we certainly have achieved our goal of providing high quality technical content. Those of you who are premium registrants, you will be receiving the Frisbee to the address that you had in your registration. There will be some further updates by email on the timing and so forth of this, but it is coming. And finally, well, almost finally, I have to make a very big special thanks to our sponsors. Even for a virtual conference, our sponsors are what allow us to accommodate all of the things that we enjoy and feel are important to this community for the conference. And finally, see you next year somewhere. We're still working it out. Maybe Vancouver, maybe online, maybe hybrid. But a special shout out to those of you who are not registered and not on our email list to regularly get things. I highly encourage you to go to our webpage in the organization tab, contact us, and add yourself to our mailing list. As we determine how next year is going to look like, this will enable us to get in touch with you and invite you to participate in all stages of the conference, from call for demand all the way to the invitation to register. And with that, the formal part of HPG is now complete. We're going to do the same thing as we did on Wednesday, and we're going to automatically disperse everyone in the auditorium to a social space and encourage you to socialize. Thank you very much.